I'm Dr. Matt Mowlem. I'm responsible for the development of the probe that's going to enter Lake Ellsworth. I'm the head of a 10-person team doing that. We're very used to developing engineering to go to depth in the sea, but the borehole which the probe must go down is actually very narrow. It's 36 centimetres in diameter when we start, and then it starts to freeze about 6 millimetres an hour. So we've got to engineer all our system that can be extracted at the end of the experiment, which means that the maximum diameter is 20 centimetres. And that means that inside the pressure case, that's how big everything has to be. That's an actual piece of electronics that's going to go on the probe. And that's the size that we have, the working space inside the pressure cases, inside the vehicle. So that's a real challenge to get all of the sensors, all of the communication. We've got videos, lights, water samplers, sediment samplers, get all of that technology packed into that very small diameter. There are two sampling systems on the probe. There's a water sampler and a sediment sampler. The water sampler is many of these. So this is a bottle that captures the water. They are very heavily engineered because the water is completely unknown. We don't know what's in the water in the lake. There could be very high gas content, and so we want to capture not only the liquid but any gas that's also at pressure in the lake. So this maintains the pressure of the lake, which is 300 atmospheres, so 300 times atmospheric pressure, brings that pressure to the surface, the water at that pressure to the surface, and then can be opened in the laboratory for analysis. Now, that's never been done before at these temperatures, so we've had to build a rig for testing every element of that design. This is a rig for testing a magnetic coupling, which is the way in which these bottles are opened and closed. That's triggered from the surface via the fibre optic cable. A little motor turns. It's protected from the environment by a shield linked with a magnetic coupling. And then the water enters the bottle at full pressure, and the gas is held within it. When it comes to the surface, it'll hit -18, so the water inside that bottle will freeze. So it was at 300 bar when it went in, it becomes 2,700 bar, so 2,700 atmospheres of pressure of frozen water inside the bottle. This bottle is made out of grade 5 titanium and can withstand that pressure without breaking. The other samplers on the system are the sediment sampler. So that's a tube that pushes into the sediment and grabs the first few centimetres of the lake bed. And that's interesting because the biology is probably going to sit in that interface between the water and the sediment. And so we're hoping we will find new biological species in that top layer. And then the rest of the probe has a number of cameras. And so there's one on the top looking up at the hole that we've made in the ice. You can have a look at the underside of the ice sheet to see what that looks like. That tells us information about the glaciology. And it's got a camera looking down to give us pictures of the lake bed, see if it's rocky, if there's anything there of interest. And then we've got sonar on the vehicle to tell us where it is at all times, and a number of sensors. So we're measuring conductivity, temperature, the depth, we're measuring the dissolved oxygen content, and then we're looking for chemical parameters like pH and EH, the redox potential in the water. So all of that data is coming back up a wire. Actually, it's coming up a fibre optic cable. There are 6 fibre optic cables in a tether, and we can, if one of them breaks, we can swap to another one. And that data comes up to the surface where this computer package stores and displays the information for the scientists to have a look at and to look at in more detail after the experiment's over. It's one of the big challenges of the project is that we're breaking new ground in a number of areas. We thought a number of the things had been tackled, and we go to the web and to the literature and to look up how these things are done, and they just haven't been done before. So the sterility aspect is definitely one of those. There are some things we can learn from the medical industry and from the space sciences, but we are doing new things that have never been done before in new ways, and that's a really great part of the project. It's going to be a very nerve-wracking, nail-biting moment when we launch the vehicle. We've only really got one, possibly two chances. It has to work first time in very extreme conditions, straight out of the box, and we can't have got it dirty in between. So there will be no fiddling with it, mending it in Antarctica after shipment. It's got to be perfect, boxed up here in the UK, and once it's in its container, that's it until it's broken open, ready for the experiment, which all has to be completed in 24 hours.